continuity worksheet. So let's go through this. Number 1, find the points of discontinuity of the function shown in figure 14 and say whether it's left continuous, right continuous, or neither at these points. So our continuity, just being continuous just means like your solid line, like right there. From here to here, we're continuous. Then we get to an issue at 1. At 1, we're not continuous. It's not a solid line. We can't like draw it without picking my pencil. So 1's discontinuous. So there's a discontinuity at 1. So discontinuous at x equals 1. Now is it left or right continuous or neither? That just means which side has the solid point. So like right here, right? The left side has a solid filled in value. So that's left continuous. But is left continuous? So there we go. And then we keep on going. So again, so it's not continuous there. It's continuous from here to here, right? It's all nice and solid. I could draw that perfectly. Then we have an issue again at 3. So it's discontinuous at 3. So discontinuous at x equals 3. And in this case, it's neither. Neither side has a solid dot. So it's not left or right continuous. The dot's down here, so it has nothing to do with the continuity of it. So neither. Okay, then we keep on going, right? So continuous until we get to 5. At 5, we're discontinuous again, and it is left continuous once again. And then left continuity, but left continuous. So there you go with that part. Then we go to the next problem. Find the points of discontinuity of f of x and say whether f of x is the left, right, or right continuous or neither at these points. So just like the question we just had. So we'll go faster here, right? So at 1, we're discontinuous, and it's left continuous. At 3, we're discontinuous. That is discontinuous. You can't draw that without picking pencil. There's a hole right there. So that's discontinuous right there at 3. And it's a neither, not left or right. And then at 5, we are right continuous at 5. So from the right, you have a closed circle. So it's discontinuous at x equals 1, x equals 3, and x equals 5. 1 is left continuous. 3 is neither. And then 4 is right continuous. So there we go. Number 3. At which point of C does f of x have a removable discontinuity? What is the value should be assigned to C to make it continuous at x of C? So removable discontinuity is like which one could you fix easily? So right here is our removable discontinuity. We could just like fill in that hole. So what value of x? What value should we assign f of C to make f continuous at C? So we just gotta fill that hole in. So right here, if instead of being down here, that point was up here at like 4.5, then it would be continuous all the way through. So it's an easy fix. So for 3, I'm going to say x equals 3 is where it has removable discontinuity, and then we would want f of 3 to equal 4.5 to make it continuous at 3. 4, find the point of C1 at which f of x has a jump discontinuity, but is left continuous. Well, what value should we assign to f of C1 to make f a right continuous at C1? So we want to find out the point C1 where we have a jump discontinuity, so one of these guys, either this guy or this guy. We want it to be left continuous. That's over here. So at x equals 1, so this is for 4, x equals 1. That's where our jump discontinuity is. What value should we assign to f of C1 to make it right continuous? So right now, all I mean is this, like f of 1 currently equals 2, and that makes it left continuous. Well, we'll have to change that to make it right continuous. We'll have to make its number right here, so 3, to make it right continuous. That's all they mean. At x equals 1. So there we go. 5a, for the function shown at figure 16, determine the one-sided limit at the discontinuity. And I don't have figure 16 here on my picture. I'll make sure to fix it for you guys. So I just gotta draw it myself. And it looks kind of like this. Let's see, here's my line. It's not gonna be the best picture, but I just want to get the idea. This graph looks like it goes like this. Here is 6. Here is 2, open circle. Then it kind of bends up, and at 6 is an open circle, and goes this way. And there's at 2, there's a point right there. So that's my best estimation of what figure 16 should look like. And you guys will have it on your paper. For a function shown in figure 6, remember the one-sided limits at the point of discontinuity. So they want the one-sided limit like right here. So what's the left side limit? What's the right side limit? Remember the way we do that? So we go limit as x approaches 0 from the left of f of x. I'm going to say the limit as x approaches, that's a bad one. Go up here. Limit as x approaches 0 from the right of f of x. I'll get the one-sided limit at 0 here. Now, as you approach 0 from the left, look at my graph, it's going up to infinity. So my answer there would be infinity. And as you approach 0 from the right, so here's 0 if you come from the right side, it's getting to 2. So there's my one-sided limits. If I was going to do this one, I'll leave this out for now, but like the left side limit here looks like it's going to be 6, right side limit looks like it's going to be 6. So to remove discontinuity, both sides match, 6 and 6. So let's go to B. Which of these discontinuities is removable? How should it be? I feel bad. Okay, so part A here. I should have done limit as x approaches 2 from the left of f is 6. The limit as x approaches 2 from the right of f is also 6. I should have done that. Okay, now we do B. Which of these discontinuities is removable? Now should f be redefined to make it continuous at that point? So this is the removable one, right? It's an easy fix, just fill in the hole. So at x equals 2 is removable. How do you fill it in? Well, just instead of having it be down here, make it be the point right there. That'll be nice and connected. So we say f of 2 should be 6. There we go. And if you do that, then it's a nice continuous function the whole way. So let's move on. For 15 and 16, use the laws of continuity in theorems 2, 3 to show the function is continuous. So he's going to say why these functions are continuous. The general rule is if you multiply two continuous functions, it's continuous. If you take the composite two continuous functions, it's continuous. So he's got to use those two things. So in this case, f of x is continuous because it's a product and composition of the known, that's an n, continuous functions e to the x, right? We know e to the x is continuous. The re-x, right? The function inside there, and then cosine x. So that's why we know this function is continuous. Because right here, this is a composition of functions. The re-x is inside of cosine. As long as 3x is continuous, which it is, it's a line. As long as cosine is continuous, it is, it's like the sine graph, cosine graph. And then ex is continuous. So they're all continuous. So as long as you do the composition or multiplication of them, it's all continuous. Same with 16. Now this is just composition of functions. So all you're going to say is f of x is continuous because it is a composition of natural log of x and x to the 4th plus 1, which are known continuous functions. And x to the 4th plus 1 is greater than 0. So there we go. So there's those two. Let's move on. Determine the points at which this function is discontinuous. State the type of discontinuity, removable, jump, or infinite, or none. Okay, so we get into our basic graphs here. So 1 over x is a reciprocal function graph, so it looks like this. So what type of discontinuity? Well, first where's our discontinuity at? Right, it's red 0. Right, that's the only spot I could draw it and not pick up. You saw me do it. I had to pick up my pencil, right? So there's this graph. That's all continuous. This is all continuous, but between the two, I can't connect them. So that's the discontinuity. It's at x equals 0. We have a choice. Is it removable? No, that's like the fill in the hole one. Is it a jump? No, because that's like where you could kind of jump from one to the other. You Mario Brothers it. Is it infinite? Yeah, these are both like it's a vertical asymptote, so it's an infinite discontinuity. So there we go. So 20 here, we're going to graph it on our calculator. So I'll let you guys graph in your own calculator. I'm going to draw it from what I know the calculator says. So here's the basic graph. And if you put that in your calculator here at 2, you grab a graph that looks like this. And you get a graph that looks like this. 7 is at 1 and -1. That's less important. It should happen actually at 1 and -1, not above -1. What's important is what type of discontinuity is this, right? It's discontinuous at 2. That's where you have to like separate. If you're drawing this, you have to like stop and go up here. And this is a jump, right? I'm going to jump from there to there because I'm Mario. So x equals 2. It's a jump discontinuity. So there we go. 23. I did this one out a bit. So now this one, you can try to draw it. Now, before you draw, if you remember stuff from math analysis or algebra 2, you could actually factor the bottom. The difference of two squares. These cancel out and you get 1 over t plus 1. So what happened there is we had a hole at 1. So if I was going to graph this, it's like a reciprocal function moved to the left one. So at -1 here is our little asymptote. Graph like this and like that. And then we had a hole at 1. So at 1, we have a hole. So there's two types of discontinuities here. We have an infinite one at -1, and we have a removable one, a hole, which is removable at 1. So removable at x equals 1, and then an infinite at x equals -1. Next one. This one again, we could graph it. If you'd graph it, from your calculator, do the rational root. You do rational roots. I'll tell you right now, it's at 1/2 rational function graph. It's at 1/2 asymptote, and I believe it looks like this, like that. So we're gonna have an infinite one at 1/2. There we go. Let's move on to 53. So 53 to 56. Draw the graph of a function on 0 to 5 with the given properties. F of x is not continuous at x equals 1, but the limit as x approaches 1 from the right f of x and the limit as x approaches 1 from the left exists and are equal. So these are questions I love to give on the quiz and test. So f of x is not continuous. So when we do one of these, this has to be true. Sorry. That part has to stay true. So it can't be continuous at 1. So if I was drawing a picture, at 1 it can't be continuous. That's very important. But this is the left and right limits of 1 do equal each other. So to me it looks like a graph like this. That's a hole. It's a removable discontinuity, right? So it's not continuous, I can't draw it, but the two limits on both sides match. If I was trying to do a jump graph, the limits on either side wouldn't match, so I can't do that. So the limits on both sides have to match, and then it's not continuous, so it's a hole. So since that effect. If you want, you got a little point somewhere. Doesn't matter. 54. F of x is left continuous, but not continuous at x equals 2, and right continuous, but not continuous at x equals 3. So let's draw this. So here's 2 and here's 3. So it's left continuous. Remember, all that means is on the left side, it's filled in, but not continuous at x equals 2. So at equals 2 is not continuous, but it is left continuous. So I'm gonna have the tail go from the left side, start somewhere else, go like that. Right, so this is not continuous, but it is left continuous. So the left side has filled in value. And right here it says and right continuous, but not continuous at equals 3. So I'll have this go somewhere. It has to be right continuous. So wherever I draw my extra point, it goes to right. Again, that's only one example. I could do so many different versions of this. If I wanted to, I could draw something like this. Close circle this way, open, open, close circle this way. I could put the close circle, I could put this line up here and go in that way. There's so many different options. I just do one or two of them. So there we go. So again, left continuous or right continuous, not continuous at that actual point. f of x has to remove this continuity. So if I see those words, it's just vocab. It's a hole. At x equals 1. So we have a hole at x equals 1 and a jump discontinuity at x equals 2. Now I don't need to translate jump, it's pretty self-explanatory. So jump at x equals 2, and then give some more information here. The limit as you go from 3 from the left is negative infinity. The limit as you go 3 from the right is 2. So a lot of stuff we gotta add on to here. So what do I care about? I care about 1. I care about 3 and 2. Man, this graph's not helpful at all. Let's do something like this. All I need is the right side. That's not straight. Here's 1, here's 2, here's 3. I was just trying to give myself a little more space on the 1, 2, 3. So we have a hole at 1. So let's draw a hole. Boom. Then probably connect a little. There we go. Again, I'll probably flesh it out more, but just for now, we have a hole at 1. We have a jump discontinuity at x equals 2. So at 2, we have a jump discontinuity. You can do it any way you want. So like that, right? Jump. If you want to fill one in, you don't have to. Then right here it says 3 from the left is negative infinity. 3 from the right is 2. So let's say this is 2. So 3 from the right is 2. 3 from the left is negative infinity. So we have to go down, let's pretend I put like a little asymptote right here so you can see it. Not really there. Right? As you come from the left side, you have to go down to negative infinity. So I have to turn this guy all the way down. Something to that effect. Keep in mind, it should be a function, right? Notice I don't have anything overlap. All this passes the vertical line test. I mean, theoretically right here passes the vertical line test. So something like that. 3 from the right gets you 2. 3 from the left goes all the way down to infinity. Personally, I like it a little better if I drew that line a little nicer. Maybe this can be a little smaller. Something like that. Looks a little nicer now. Let me finish off this side also. And that side. There we go. Right, so it's a function. And right here you have a hole at 1. Right here you have a jump discontinuity. And then here you have one side going this way and one side going there. Again, you can change it up a bit. I could add a little point above this guy. I can make one of this side like left continuous. Whatever works. As long as it passes the vertical line test, good. 56. F of x is right, but not left continuous. So again, right there, something like this, right? Something like that. But it's right continuous, but not left continuous. So it means the right side is filled in. So in my head, that's a picture I see when I read this. It happens at 1. Left, but not right continuous at 2. So at 2, it's the other picture. And neither left or right at 3. So at 3, it's going to be this like open, open. So now we just combine that all into one graph. One graph that passes the vertical line test. Very important. So here's 1, here's 2, here's 3. So again, 1 is right but not left. So the left side shouldn't be it, but the right side can be filled in. And then at 2, we're left but not right continuous. So wherever I want to, again, it's up to you, but wherever you want to draw this graph go, make sure it's left continuous but not right continuous. And at 3, it's neither continuous, so both should be open. So at 3 should be like this, and then maybe I start right here and go down. Something to that effect. Let me erase this because it's cluttering the picture. Right? So again, notice how it passes the vertical line test. Right, even right here, right? That's an open circle, doesn't count when closed. That's not a very good straight line. There you go. passive vertical line test, it all works. 1, we're left continuous, we're right but not left. 2, we're left but not right. And at 3, we're neither. So perfect. 57. Each of the following statements is false. For each statement, sketch the graph of a function that provides counterexamples. So key thing to keep in mind here, each of these is false. This is not a true statement. So A, if the limit as x approaches a of f of x exists, then f of x is continuous at x equals a. So what this is saying is, if the limit exists, then it must be continuous. Right? And this is a false statement. So the way this works, when you do a counterexample, you got to make this part true. And you got to show this second part is false. Show false. So limit does. So I can't draw something that's not continuous. Say, oh, the limit doesn't exist. No, we got to go with the if part. Make the if part true. So the limit has to exist, but just can't be continuous. So what's an example of that? Well, something like this. Right? This is not continuous because there's a hole right there, but it is. The limit does exist because the limit from the left side matches the limit from the right side. Right? Only time that happens with discontinuity. Only time the limit exists when it's discontinuous is there's a hole in the graph. So there's A. Done. B, similar idea. If f of x has a jump discontinuity at x equals A, remember that's the part we have to make true. So whatever we draw here has to have a jump discontinuity. Then f of A is equal to either limit as x approaches A from the left or limit as x approaches A from the right. So they're saying that if you do a jump discontinuity, either one of the sides has to be filled in. That's all this is saying. That's not true. Or I could do a jump discontinuity like this. That's still jump discontinuity. F of A could be like up here somewhere. And that's still good, or there doesn't have to be an f of A. So this is a counterexample to what you see there. So again, when you're doing these counterexamples, you gotta make the if part true. So it does have to be a jump discontinuity at A. And you're trying to show that this part is not correct. You gotta give an example where based on this second part's not correct. Next one. Sketch the graph of the given function at each point discontinuity. So whether it's left or right continuous. So we want to draw a picture of these. This is why it's in our calculus, a pre-calc test. Our calc readiness test, if I could talk. So a piecewise function. So x squared, but we only want it when it's less than 1. So if you're new to drawing piecewise function, trying to review, remember how to do it. The actual key part, like we know what an x squared graph looks like. It looks kind of like this. But we do want to know where this one's important. We know where that hits at. So easiest way to figure out how high I should go is plug that into the equation. Plug 1 into x squared, and I get 1. So 1 and 1 is where my graph hits. And the rest of it's a parabola. I don't need this part. And look at this one. See how it's actually equal to right there. So I should have filled that in before I changed my colors. So there you go. So that's filled in. Now we draw the next one. 2 minus x. I've always preferred to write it as negative x plus 2. Right. So y-intercept at 2. Then we go down 1 over 1. Actually, it's the same spot actually. And then we just connect it. But again, it's a piecewise function. I only want the part that's greater than 1. I don't need this part. That was a mistake. I need that part. That was a mistake. I'm gonna leave it like that. And we get this. And look, it's all nice and connected. I mean, it's not that we'll talk about that later, but it's all nice and connected. There's no jumps here. It's just our holes. It just connects and flows. Right there, remember, it was an open circle and a closed circle. Anytime you have that, the closed circle is this one. So it's just a closed circle. You can't be both. So there we go. This is continuous everywhere. Okay, next one. X plus 1 for x is less than 1. 1 over x for x is greater than 1. Now let's start with the 1 over x for x is greater than 1. So 1 over x looks like this. Now I only want it for where x is greater than 1. So I actually only want this side. Remember, like I said before, the 1's important though. Like, where does that happen? Is it 1 in 2, 1 in 30? What is it? Just plug it in. Plug 1 into 1 over 1. 1 over x, for which it's 1 over 1, so just 1. So at 1 and 1 is where my graph's going to start, and then you just do the right hand side. So something to that effect. The one up here, x plus 1. We know how to graph that. That's a y-intercept of 1 and the slope of 1, up 1 over 1. So like that. And actually should be an open circle. Shouldn't close that in. So right here. I'm a little off actually, like right here. That's where 1 is. So we went up 1 over 1. And again, if we connect this line here, I only want the left side, so I'm just going to connect this side. Like that. So there's my piecewise function. I have my orange graph right here, and I have my blue graph right there. And what type of discontinuity is this? Because it's not connected, it's a jump, right? To go from there to there, you gotta jump down. So it's a jump at x equals 1. And it's right continuous. Because the right side has a closed circle. That's all that matters. That's the easiest thing about right side is closed, so it's right continuous. Let's do this with a couple more. So absolute value of x minus 3. There's another not straight line. Absolute value of x equals 3. So inside opposite, and go to right 3. 1, 2, 3. Normally absolute value looks like this. Ish. But I only want the part that's less than or equal to 3. So starting down here, I'm going up. Here's my graph. I don't need this stuff. Okay. And then the other graph, x minus 3 for x is greater than 3. So let's go down to negative 3. Start there. And then the slope of 1. So up 1 over 1. Up 1 over 1. Up 1 over 1. Start there. And going to the right. Again, it's closed and open, but closed wins, so it's this nice connected graph. This is continuous everywhere. Right, it's all nice and connected. Looks just like an absolute value graph. Next one, 83. It has a slightly different. It's actually a different direction that I forgot to put here. It's find C such that f of x is continuous. This is one of my favorite questions. I gotta find C such that these are continuous. What does that mean? That means when I plug 5 into this, I should get the same number. When we're continuous, that's what happens. Like right here, we're continuous, right, at 3. So when I plug 3 into here, I should have got the same number. 3 minus 3 is 0. 3 minus 3 is 0. They matched. Up here, when they weren't continuous, if I plug 1 into both of these, they're not going to match. When it's there, 1 plus 1 is 2. 1 over 1 is 0. The reason we had to draw it is to find if it's a jump or a hole. So don't get mad at me. Look at this one, right? Plug in 1, you get 1 squared is 1. Plug in 1, you get 2 minus 1 is 1. So they're continuous at that point when you sub them into the formula and they match. And they're not continuous when they don't match. You do have to graph it to figure out which problem it is, though. Which discontinuity it is. So the first thing I'm going to do is plug 5 into both of these. So I'm going to go 5 squared minus c, and 4 times 5 plus 2c. Now if I want them to be continuous, I want them to match. So you set them equal to each other. That's all we have to do. Set them equal to each other, because that's when they're continuous, they match, they equal each other, and then plug the value in for x. And now we can solve for c. It's an algebra 1 problem. Minus 20 plus c. I get 5 equals 3c. Divided by 3. C equals 5/3. So that's the value of c for which where this function is continuous. So now we're going to try the same thing with 84. Right? So I want it to be continuous, so I'm going to set them equal to each other. And then I want it to be continuous at 3 specifically, so plug 3 in for x. So I get 6 plus 9 equals negative 12 plus c. So 15 equals negative 12 plus c. Add 12. C equals 27. So that's the value which f of x is continuous. Okay, down to the home stretch here. 86. Which of the following quantities would be represented by a continuous function of time, which would have one or more discontinuities? So all they're saying is like with respect to time, would this be a continuous function? Velocity of an airplane during flight. So all it's saying is like, if you're flying, does it go like, hey, does it climb up and then all of a sudden like shoots up to the higher spot? It's like if you're driving, you don't ever like go from 80 to 100, go from 40 to 50 like off the bat. You have to go all the values in between. So this is continuous. You can't just jump speed values. So continuous. Temperature in a room at ordinary conditions. Same concept, right? You don't just ever have, when you turn on the air conditioner, it doesn't just jump down 5 degrees. It goes down gradually. So continuous. Value of bank account with interest paid yearly. So here's the key. It's paid yearly. So that means like, let's say you have like a 10 grand in your account. And at the end of the year, they put in all the interest. Because it's yearly. So then you have like 11 grand in your account. Let's give an example. Right? So that did take a jump. So this would be a jump. They just put all this money in at once at the end of the year. Most banks do continuous investment, so it actually goes more continuously. But if it's paid yearly, then it's a jump. Salary of a teacher, maybe you don't know this, but your pay doesn't just increase throughout the year. At the end of the year, you might get paid more because you've been teaching for an extra year, so now you get like a salary bump. So that'll be a jump again. Most times it did. Population of the world. That's a little. It depends how you see it. It's how do they count it? I would say most of the time they count populations. They do it like yearly. They don't do it like every single continuously. So this actually be a jump. But I could understand if you wanted to say like continuous. So technically it's a jump because we don't just take populations like every second of the day. Okay, last 3 questions. Suppose f of x is less than 0 if x is positive. So that's saying here's x, here's y, or f of x. If x and y are the same thing. So they're saying if x is positive on this side, my function is negative. So something like this. That's what that's saying. And f of x is greater than 1 if x is negative. So when we're negative, f of x is greater than 1. So something like that. Can f be continuous at x equals 0? No. How do you skip past the neutral numbers? No. There's a jump. No, f cannot be continuous. There will be a jump at 0. If you want to go a little more detail, because the limit of the left side has to be positive, the limit of the right side has to be negative. Are the following true or false? If false, say the correct version. A. F of x is continuous at x equals a if the left and right hand limits of f of x as x approaches a exist and are equal. So what they're saying is that it's continuous if the left and right hand limits exist and are equal. Well, if I do this, right, the left hand and right hand limits exist and are equal, but it's not continuous. So to fix this, you have to also say and f of a equals the limit as x approaches a of f. Right? It also has to have the value to make it an actual continuous function. So this was wrong, how to fix it. F of x is continuous at x equals a if the left and right hand limits of f of x as x approaches a exist and is equal to f of a. Well, yeah, that's the fixed version. So yeah, this is true. It's kind of anticlimactic. Anyway, that's it.